Okay, thank you everyone for joining on Saturday morning to join the journal club. My topic today is Sora. Sora is a very powerful text-to-video application developed by OpenAI, and it can generate around 1-minute video. I asked ChatGPT, in short, what is the meaning of Sora? ChatGPT responded that, in short, Sora means sky in Japanese. So they named this application or model as Sora because it wants to represent its limitless creative potential from text to video. However, the technical details of Sora is not fully disclosed. We can still use the reverse engineering to try to see what could be the possible framework. By implementing the techniques in this framework, you will be able to create something like Sora, although you may not be able to achieve the same performance as Sora. Actually, this session is the second session of Sora series. Last session is presented by Sean, and he introduced how to convert the pixel video space into the lower dimensional latent space, and how to pre-process those videos into latent space and patches. Our session will focus on the conditioning part. The conditioning is by input the ChatGPT augmented prompts and potentially the image prompts, which will go through the clip-like model and to create the embeddings, which will be used to guide the later video generations process. Let me get my laser. Okay, so let's have a closer look at the conditional section. You can see that the human instruction or images input will go through the system, go through the clip model, and guide the video generation part. So we may have some questions. First, what is this model, which is clip-like model? What is it? And second, how do we use clip in the conditioning process? And third, why do we need the prompt augmentation here? Keep those questions in mind. Hopefully, after this session, you will be able to answer those questions. So first question, what is clip? Clip is the contrastive language image pre-training. You may feel like you understand every word here, but you cannot understand what is represented. First, the concept constructive. Constructive learning actually is very simple. When you are very young, how do you learn things? For example, if I give you a task, I give you a dot image here, and I ask you, can you pair the most similar image from the right-hand side group? I guess so, right? You should be able to pair that this image looks most similar as the one that I gave you. If you think it doesn't make sense, maybe you can consult your elementary school student. And what if I change the image into text? Can you still be able to pair? I think you still be able to find that the white dog, this text, is the most similar to the image. So the contrastive learning actually is to compare the features of one group of one content and compare the features with a group of content to find the most similar one. So the contrastive language image is the contrastive learning between the image input and the text input. So CLIP is a pre-trained model that would tell you how well a given image and a given text fit together. This model is released in April 2021 by OpenAI and is open sourced. It's built on 400 million image text pairs, and the input is an image. The output will be the best caption as what we have done in the exercise to pair the most similar image and text pair. It has zero-shot capabilities. We will talk about this in detail later. What is zero-shot? So let's have a look at the training process of CLIP model. First, we prepare n text, and n images as one batch. This batch of data will go through the text encoder, which could be the transformer, and to transform the text into embeddings that the model can understand. For the image encoder, we also encode those images into embeddings through like ResNet or Vision transformer. So here you can see we have n embeddings. Each of them represent one text content here. Same for the images. We have n embeddings for images, and each cell here also represents one image. For all those, after we have n embeddings for text and n embeddings for images, we can create n squared pairs between them. And only n pair are the correct pairs, which is represented in the blue cells, diagonal blue cells here. So our objective is we want to learn the weightings. We want to construct the text encoder and image encoder that can construct the embedding to maximize the cosine similarity of the image and text embedding of the correct pairs, while minimizing the incorrect ones. By doing so, we can create the text encoder and image encoder that it can encode those texts and images into the same latent space. That is the training process. If you have any questions, feel free to raise your hand anytime. So after we train the model, which can find the most similar image and text pairs, how do we use it in inference? For example, we have an image, which is a dog image. However, imagine that we don't know the class of this image. We want to know, is this image a class? Is this image or dog, or a plane, or a car? In other words, it's an image classification task. What should we do? We can list down the names of all the classes, and we can create a prompt template, like a photo of a plane, a photo of a car, and a photo of a dog, like that. We transform all those prompts or text descriptions through the text encoder we have trained to create the embeddings. And we compare those text embeddings with the image embeddings. We can find the most similar one, which should be a photo of a dog. By doing so, we can add the label, which is the dog, to the image. So that is the image classification process. And the great thing about it is it has the zero-shot transfer capability. What is the zero-shot transfer capability? Because when you are young, when you have, for example, if you know what is a horse like and what is a panda like, and if I tell you that a zebra has the shape of horse and the color of a panda, will you be able to find the zebra in the zoo? I think so, right? Because you can combine the knowledge that you already know and to transfer it into the new knowledge. However, in traditional image classification task, which is trained on image labels, the model can only make prediction on the data that it has already seen in the training dataset. It won't be able to classify the image of zebra if it has never seen zebra before. That is the traditional image classification test model and systems. The zero-shot transfer capability means if I tell you the information about the horse and the panda, even though you have never seen zebra in the training dataset, you should still be able to predict whether an image is a zebra or not. That is zero-shot transfer capability. And as we have mentioned before, if we imagine we can input an image like a zebra, and our prompt can like a photo of a zebra, which has the shape of a horse and the color of a panda, it should still be able to predict what is a zebra. So that is the great thing about Clip. The two benefits of Clip is first, because now what we want to do is we don't need to add a specific label onto those images during training dataset. So we can make use of the online resources. We can, because for the online images, most of them have the captions or alt text to describe about those images. We can directly use those online resources as the training dataset. Otherwise, imagine that you need to manually label 400 million text image pairs. How much resources you need to occupy? That's a lot of work. By doing this kind of framework, we don't need to manually label. We can use the online resources. And second, it can enable us to do zero-shot transfer while in the inference. So that is the two benefits of creating a clip model. In summary, in training, the clip model tries to maximize the cosine similarity between the correct image caption vector pairs and minimize the similarity scores between all the incorrect pairs. While in inference, it calculates the similarity score between the vector of a single image with a list of possible caption vectors and picks the caption with the highest similarity. So now we know what is the clip. Clip transforms the images and the text into embeddings in the same space, so we can understand them and compare them. So the next question is, so what? Seems like Clip can only help you to match the most similar text and image pair, but we cannot use it to generate like an image or video or anything like that, because it's not a generative model. So how can we use Clip in conditioning and in generative tasks? Now I have to introduce you to the DALL-E. If you know the artist DALL-E, you should be able to recognize this picture, which is the melting clock. It's a very famous artwork. And you should also maybe have watched the film called WALL-E. DALL-E is named by combining the DALL-E and WALL-E, which is to combine the human artist work with the robotics. So because the function of DALL-E is to create images and art from natural language instruction by artificial intelligence. Here are some examples of the output of DALL-E. You can see that if we input those prompts or captions, the DALL-E model can generate very artist and also very realistic images. We can start, until now, the DALL-E has reached its third generation. We can start from DALL-E 2. Because DALL-E 2 is the image generation using clip latents. It's released in April 2022 by OpenAI. It uses clip to generate realistic images and art from a description in natural language, and the input is also image and text pairs. This is the structure. First, we use a clip text encoder to encode the text into clip text embedding. And then we use a diffusion prior to transform the text into clip image embedding, which will be input into the diffusion decoder to create images. If you have an idea about Glide is also a model created by OpenAI. Its usage is to conditioning on the text input and to use the diffusion decoder to generate images. Here is the modified Glide is just because we add the image embedding into the system of Glide to achieve the better generated images. This is the DALL-E 2 architecture.
Yeah, sure. Question, could you kind of elaborate a little bit more on the diffusion prior and what it does?
Yeah, that is the next steps. I'll introduce it later. So the prior in detail. What is the diffusion prior? The goal of the diffusion prior is to generate the clip image embedding. It's a decoder-owning transformer with a causal attention mask on the elements in order. The first one is the encoded text, which is the caption. And second is the clip text embedding that we transformed from the image encoder. From the text encoder. And an embedding for the diffusion time step, and also the noise clip image embedding. So it will pass the transformer to get the denoise clip image embedding until the time step 0, which is the final embedding whose output from the transformer is used to predict the denoise clip image embedding. In other words, it's the unnoised clip embedding. So this prior will help us to find the image embedding using the text embedding and encoded text as input. Is there any questions?
Do we have a kind of more intuitive understanding about why this would work?
I think so. Intuitively, you can you go to the previous slide?
Yeah.
I think intuitively you would expect, because after a clip is trained, we're trying to unclip, right? After a clip is trained, you would think the text encoder will encode things into the same semantic space with the images. But people guess, the authors probably tried that, and they realized that they probably need a neural network to convert the text embedding to the image embedding, which they use to generate the picture, to get it to really to work. So this is basically translating the text embedding to the image embedding, although they are supposed to be in the same semantic space. Adding this neural network will make them work much better. So that's people's, that's actually Brian Zhou's hypothesis, conjecture.
Yeah, I understand that, like the functionality of the whole diffusion prior is to converting the text embedding to image embedding. But if we go to the details slide, like why this, like why we use these input, and another thing kind of caught my attention is like why we are doing, like the step by step. So there is some diffusion steps. So it doesn't. So why we are doing this? Kind of like this is kind of like a diffusion, like okay, we are denoising, but why we are using the denoising approach to convert these embeddings, that might be kind of something kind of on my mind. But of course,
I see. You're asking, why do we use transformer rather than why do we use a diffusion model rather than a one-pass transformer model or a fully connected layer or something else?
Yeah, and also like the inputs, like. It looks like we are kind of continuously kind of input the encoded text and also clip text embedding these two. Like we always pass this to the model. So why we are doing that? So yeah, just trying to see if we have some intuitive understanding about this part. Like,
I think the first question of why do we use this architecture, I think it's $1 million question. My guess is people try different models, it's turned out to be working. That's why. Would other model not work? I don't think so. Maybe you can try and make them work. But I mean, this is a typical question. Why would this architecture work rather than the other?
Yeah, actually, the author also tried the autoaggressive model and compare with this diffusion model. They find that diffusion prior can get better quality and less resources, which is
we tried it.
Yeah, so they try different ones and find this works best.
Right. As for why we need the encoded text and clip text embeddings, I think it's a typical practice to condition the model output. Right? Otherwise, how do we know? Because the input is just noise, right? So how do we know it's turning into a latent that's the same with our input text? So they're just conditioned at every layer. I think it's a common practice for many generative models.
I see. And here, just another kind of very quick follow-up is like, this might be a little bit detailed, like the encoded text. What's the difference between the encoded text versus the text embedding?
So, that's a good question.
I think it's about. Yeah, go ahead.
I guess the caption, the encoded text here is just a simple encoding into the simple encoding of the text into the vectors. But the text embedding is to use the clip encoder to transform the text encoding to transform the text into the embedding space that we used in clip. So I think the encoded text has more raw data. It's more like the caption, but the text embedding, you already transform it into the space that you trained. So the encoded text should have more original information.
Cool. Yeah.
So my understanding is encoded text is a supervisor, right? It's not a trainable model, and the clip, of course, is trained, so it has more embedded information, but they are different.
Yeah.
Yeah, that sounds good. Thank you.
Stupid question. Where do you find this diagram?
You mean the diagram?
Right. I know
This diagram.
Medium. Where did they cite it from? Which paper was it from?
This diagram is from the Medium.
Right. That's from the Medium, right?
Yes,
I was wondering where
created by the author. It's not in the paper. So, because in the paper, the author doesn't dive deep into the details of the prior, and it's just the description here, the text description here is what we have in the paper, and so the diagram here is the author in the Medium who wants to try to understand it better.
Mm-hmm. Gotcha.
Okay. So actually, prior is not strictly necessary for image generation. For example, we can try to train the model using only condition on text caption. And we can also try to condition on text caption and text embedding. We can also try to condition on text caption and image embedding with the existence of prior. We can see that actually condition on text caption and clip text embedding, the results still make sense to us. But the author find that if we use prior, we can generate better results and more diverse images. That's why the author thinks at last we should use the diffusion prior. So in summary, what is DALI 3? The upper part actually is clip. We input the image and we input the text. We encode them using the clip object objective to encode those input into the same latent space. And after we complete this part, we use the lower part, which is the architecture we have learned before, to generate text conditional image. And this step can be called enclave, because basically it's invert the clip embedding into the generated images.
Can I make a quick comment? I looked through the paper and the Medium article. I think the paper mentions that the prior is strictly a probability density function of the y given the clip embedding. It didn't mention the encoded text, which I don't think makes sense because.
Yeah, I have also read the paper.
Right.
In some part, it mentions that it will put the caption and the text embedding both into the model.
I didn't find it.
Like this part, the prior part. You see, we also condition on text caption and clip text embedding, and the caption should be encoded caption we mentioned here, which is the encoded text.
So basically, they have two encoders, one encoder. I mean, because they have one encoder which encodes everything into clip embeddings. I was wondering, do they train a separate encoder? They have two encoders. One encoder dedicated for this one, or?
That part is not mentioned.
Right.
In the paper.
Right. Yeah.
But I think this topic is related with the classifier-free guidance. They think that when you are conditioning on something to generate images or generate something like some other things, instead of only conditioning on the embeddings you encoded, you should, if you also use the original information, like just pure encoded text, it will increase the diversity and performance.
Right. Maybe caption is just pre-trained embeddings of the text itself without doing the clip.
Yes.
Okay.
And as you can see here, this looks like a slightly different from the architecture we see, because the first one represents the autographic. So they tried these two and find that the diffusion one works better, and that's the one they used in the end. Okay, so that's DALI 2. DALI 2 shows...
Autoregressive means they concatenate the two embeddings from the text and image, and they just train them to generate the predict the next token based on the previous one?
Yeah, similar like that. And so DALI 2 shows an example of how to make use of clip to generate images, conditioning on the text. The third question is, why do we need prompt augmentation? Here, you see the ChatGPT augmented the human instructions. Can we just ask the human to get the prompt and to input into the clip? Why do we need this? Talking about this, I have to introduce DALI 3. If you compare the performance of DALI 2 and DALI 3, you can see that the...
Lexi, if you don't mind. Can anyone, so anyone online, do you have any questions? I'm actually not sure if the audio is working today, so if you guys want to talk, just to say no questions is fine. Anyone online there? Jixing, do you have a question you want to ask, or can you just help confirm you're good? All right, thank you.
So if we compare the performance of DALI 2 and DALI 3, you can see DALI 3 improved a lot. And what's even better is in our modern text-to-image models, the model also always tends to ignore some details in the prompt. You may even experience it in ChatGPT or other Gen AI systems. The good thing about DALL-E is it can pay attention to the details and following the prompt. The DALL-E 3 is released in September of 2023 by OpenAI. It's available in ChatGPT. Compared with DALL-E 2, it has an increased capability to generate images that exactly adhere to the provided text, without the tendency to ignore words or descriptions. And how is that achieved? It's achieved by creating an image captioner to transform the image captions. As we have mentioned before, the text and image pair that we find online in the alt text or title of the images or the captions, there are always some important details are commonly omitted, like the presence, descriptions of the objects, and the position of objects, and some common sense details, like the colors, the sizes of the objects in a scene, and the text that is displayed in an image. For human being, the color of a desk and what is the desk looks like makes sense to them, so they don't need to explain. But for model, they have not this kind of common sense knowledge. So that could be a problem for model to understanding the word. And there are also some incorrect captions. For example, it's common to find the advertisements and memes inside of the alt text. So we want to recaption the captions of the images. For example, we have 3 images here, which are the online images, and the ground truth caption, which is the alt text of those images, are pretty simple. There are not much information related with them, and there are even some advertisements. So DALL-E 3, they created 2 captioners. One to create the short synthetic captions, which is a short description about the image. And the other one is the descriptive synthetic captions, which will include all kinds of details about the images and the objects in that images. By using those captions, we can create the text-to-image models. For example, we train 3 text-to-image generation models using the descriptive synthetic captions, short synthetic captions, and ground truth captions. We evaluate those 3 models on ground truth captions and also on descriptive synthetic captions. The CLIP score is the cosine similarity between the generated image embedding and the caption embedding. If it's higher, it means the performance is better. We can see that while evaluating on the ground truth caption, the descriptive synthetic captions model and the short synthetic caption model performs better than ground truth captions. While evaluating on descriptive synthetic captions, the model that is trained on descriptive synthetic captions and short synthetic captions performs much better than the ground truth captions. So by comparing those performance, you may think that, oh, we should just go with the descriptive synthetic captions because apparently it performs the best. But actually, DALL-E 3 is trained with a mixture of 95% synthetic captions and 5 ground truth captions. Why? Because if we only use the synthetic captions, we may overfit to the regularity in the generated captions. For example, when the model generates the captions, it's very likely that they start with A or N to describe an object. and it may have certain length, preference. These kind of regularities, if we only use the all synthetic captions to generate the model, while in the inference, if you enter the prompt that is very different from those kind of structure or format, you may find that the model cannot understand what you are talking about. But the ground truth captions are generated by human beings. So this is very likely to be similar to the distribution of human prompts. That's why we want to mix the synthetic caption and ground truth caption to generate the model, because we can make the model see more diverse input and also maintain the good performance. But still, even if we blend 5% of ground truth text, it could also be possibility that the model will naturally adapt to the distribution of the descriptive captions, which is longer and more descriptive. Here, during inference, we can use ChatGPT to upsample the human prompts, which could be very simple, to descriptive captions. For example, the first row is a brief caption or brief prompt to generate image, and the second row is upsampled by ChatGPT. So the existence of ChatGPT may actually is also a very important part to increase the importance of DALL-E 3. For example, you can ask the ChatGPT to generate a model, to generate an image for you, and maybe the ChatGPT will create several different kinds of versions of prompt to upsample it and to generate images for you. But the question is, how is the image caption created? This also links back to the clip we have learned. And it's possibly using the contrastive captioner that created by Google. The COCA is a modified encoder-decoder foundation model that trained with both the contrastive loss and the captioning loss. Our input is also image and text pairs. We can try to understand it by separating the contrastive objective and captioning objective. So first, we use the image encoder to encode the images into the image embeddings, which is the blue squares here. And we use the unimodal text decoder to decode the text. Here you see that the decoder part actually is separated into two parts. One is the unimodal text decoder. One is the multimodal text decoder. For the unimodal text decoder, for contrastive objective, we append a class token in the end and use the output, which is the predicted class token, as a global representation of the text input here. While for those image tokens, we also pool them into one global representation token as the global representation of the image. By comparing those two global representations, we can compute the contrastive loss, which the idea is similar as what we have seen in the clip part. So this contrastive objective help us to understand the global meaning of the text and input. After that, in the multimodal text decoder stage,
Lexi?
Yes.
Can I ask a question? So I just want to understand, what are the differences between these tokens and the clip embeddings? Are they similar?
In Clip, actually, we have two encoders. But here, this is a text decoder. I think the reason that it uses decoder instead of encoder is possibly because after the introduction of Clip, we find that the decoder model can better understand the text, and which is better in large language understanding. And that could be the reason why they replaced the encoder into decoder here. So that is the contrastive objective. And in the captioning objective, the multimodal text decoder will cross attention to all the image encodings and text encodings to generate the captions. So in the multimodal text decoder, we have the cross-attentional head, while in the unimodal text decoder, we remove the cross-attention part. We only have the self-attention on the text. So by using this kind of structure, the model can not only understand the global meaning of the image and the text, but also it can generate the captions using the image output. Because in Clip, as we have, if you have a memory about it, in Clip we only be able to find the linking between the image embedding and the text embedding. But we cannot be able to give you an image and ask you a question related with that image, and you give me the answer I ask you what is on the left side of this kind of dog, and you should be able to answer it is a dog. In Clip, we cannot do so because we don't create joint representation between the text and the image. However, in COCA, it jointly understands the image encoding and text encoding. So it will have better capability, and it will be able to generate caption based on the image. That is how is the image captioner created.
One quick question is what's the captioning loss?
The captioning loss is to compare the caption generated with the input text here. So because you want to generate the captions based on the images, and you want it to be as similar as the ground truth. So by comparing those two, you should be able to calculate the loss, and to by minimize the loss, you will get the text decoder that can generate the best caption that fits the image.
Oh, so you're saying from the multimodal text decoder, we wanted to generate some text which is as close to the text input as possible, right?
Yes.
I also have a question. What kind of loss did you use for captioning laws? I don't know, basically, do they convert them to embeddings and calculate a distance? Do they use something like I don't know. What kind of loss do they use?
Let me think about it. So I forgot what kind of it. I think they used some language model loss, and let's have a look.
By the way, this is totally what we expect to happen, that a group of people to get together to look into a paper together. This is totally what we expect to happen during this session. Oh. Interesting. This is contrastive loss, I think, right?
The contrastive loss in the contrastive objective.
Right. This is contrastive loss,
It's
not the
just
captioning loss. we're looking for the captioning loss?
Cross entropy.
Cross entropy. Ah,
Okay.
wow, very strict.
Cross entropy of each word. Wait, something like that.
Yeah.
Interesting. So if I caption that, two dogs running in the field, if I caption, in the field, there are two dogs running, like that would be totally off in that case then. Okay, thanks.
I didn't understand why.
Yes.
Yeah, maybe you can start.
May I ask the contrastive loss? So is that just like on the other direction with the caption loss? It's like we compare the generated image with the input image?
The contrastive loss is compare the pooled image embedding and the class token output from the text decoder. So it's two global representation of the image and the text.
Oh, I see. Okay, thanks.
My question is, maybe I didn't follow. So why the model doesn't overfit to the test, only overfit to the test input? Like the generated text is exactly the same to the input text, and it totally ignores the image.
You mean the multimodal text decoder?
Right.
Actually, it's cross attention on the image embeddings and the text input. So it's not ignoring the image.
Right. But if all the weights from the cross attention part are 0, then it will be ignored.
You mean here?
Yes.
So actually in contrastive learning, it's not use cross attention because it want to learn the representation of those image and the text separately. But in the text decoder, it wants to learn the joint representation of the text and the image. So it will cross attention to the image encoding and text encoding. So can you?
Okay, I think that answered my question.
Okay. And the summary of DALI 3. The improvements of DALI 3, actually the details are also not fully disclosed. What we can know from the information that is disclosed is first, it has better caption, and this is possibly achieved using COCA. And the architecture is likely to be a text condition unit latent diffusion model with 3 stages. And this model, it could possibly looks like a stable diffusion extra large, which also is a multi-stage model, which the base stage will learn the main composition in the input, while the refiner will pay attention to the details. And in the later stage, the variational auto decoder will transform those embeddings into the final image output. The text conditioning encoder that is used in the model could possibly be the T5 extra large, which is better for long text. And in addition, for DALI 3, they train their own diffusion decoder on top of the latent space learned by the variational autoencoder, which is the stable diffusion. And they find that by using this, it will get better performance on the image details like the text and human faces. And from my understanding, the additional latent decoder is put on top of the variational encoder-decoder here. And it also uses the consistency models, which is a consistency distalization process to increase the efficiency. There's also a paper named Consistency Models, by Tong. If you are interested, you can find them and have a look at it.
One quick question, actually, back to Kakao. Yeah.
Okay.
Just wondering, this is a training process. During inference, are we using unimodal text decoder or the multimodal text decoder, or we're using?
That's a great question. So the good thing about Coca is, you see, we train 3 encoders. So depending on the text you want to do, you can actually apply them on different kind of text. Wait a second. Let me change the show. Here. So in pre-training, we have this kind of structure, while in inference, it can be applicable for different texts. For example, we can use the image encoder to do facial recognition task, which is the classification. And we can use the image encoder, unimodal text decoder to align the image embedding and the text embedding in the same space. And also, we can use the whole system to do image captioning and multimodal representation.
This is really cool. Just to make sure, why do we need text input for image captioning?
Image caption? You mean this one?
Do we need the unimodal text decoder for the captioning? The last.
I think if you only want image captioning, maybe we don't need the text input. But if you want to learn the multimodal representation, you should need both.
Right. Can you go to the previous pre-training slides? How do the information from unimodal text decoder go into the multimodal text decoder? Does it go in there at all?
Yes, that's a great question. So actually, during text decoder, it will use the text embedding as input. So it will cross attention to the image embedding and the text embeddings. And ignore the class token here and the image token here.
I see. So it didn't write that, but in fact, the output of unimodal text decoder will be fed into the multimodal text decoder.
Right.
I see.
Any other questions? Okay. So why do we need prompt augmentation? It's because DALL-E 3 proves that more descriptive tests can improve the performance of image generation. So to combine all those dots together, first, we input human instructions or images, and we use prompt augmentation to augment the prompts because DALL-E 3 proves that more descriptive text can improve the generation performance. And Sora possibly use a similar caption improvement approach. And those input will go through a clip-like model, which will transform the image and the text prompts into embeddings in the same space. And those embeddings will be used to be conditioned on to generate videos. We have seen from DALL-E 2 and DALL-E 3 that how to generate images conditioning on text. And video is just similar. So that's the conditioning part of Sora. And from this session, not only you have some exposure, you have the answers to those questions, you also have some exposure to the latest advancements of OpenAI's product portfolio. Actually, they have a lot of interaction with each other. And the paper covered in this section are CLIP, DALL-E 2, DALL-E 3, COCA. That's it. Any questions? Okay, sounds good.
Any questions online?
May I ask a question about the evaluation process? If we go back, way back about the ground truth data and the generated description. Yeah, just a new question. How the evaluation was done? Was it based on input. If input is like the first on the left side is the input is ground truth, and then like how is the evaluation done?
Yeah, sure. So you see those three kinds of line actually represents three models that we trained. For example, the blue line is the model we trained on descriptive synthetic captions. So during evaluation, we will use those models to generate images and to convert those images into image embeddings. And we compare the similarity of the image embedding and the text embedding of the evaluation set, of the evaluation data here to calculate the CLIP score. Because in CLIP, what we do is want to find the most similar pair between the text embedding and the image embedding here, right? So if we want to evaluate the prompt following ability of the generated image, we can compare the generated image embedding and the ground truth text embedding. That's how they do the evaluation. Do I answer your question? Okay.
Yeah, that's clear. Yeah, thank you.
Just a quick follow-up.
Sure.
Yeah, for these two on the, just checking my understanding here, like the difference between left and the right are the text embedding, right? Like
Yes.
The left one is the text embedding of ground truth.
Yes.
Okay. In the are they using like different models for the encoder, text encoder, and the image encoder? Like, do they retrain everything when they're building these three lines?
Yes, they use a simpler version to do it.
I see. So, kind of, the model structure are the same, but they
Yes,
redo
yes.
the whole the training process.
Yes.
I see. Yeah. Thank you.
Any other questions?
My question,
Sure.
I wasn't listening, but is the COCA model is used in Sora with, but hypothetically?
COCA actually is an image captioner. And I think in DALI 3, they mentioned that image captioner is based on COCA.
Okay.
But in Sora, what we can know is it also possibly use a similar approach to improve the caption of the videos. Mm-hmm. And if that's the case, they still need to build a captioner to generate the captions. And actually, there are some other kinds of architecture that can possibly help you to do that, like a video version COCA or something like that. So we are not so sure which exact algorithm they use, okay. But the idea is similar.
Okay, and maybe my actual question is COCA open source, and so OpenAI can use.
Let's find out. COCA source code. Yeah.
And is the trend weight is open
the
source?
checkpoint or it's the code?
Yeah, just some people try to implement it.
Yeah, I don't see
Just a trend.
Hugging Face. Yeah. Yeah.
Okay.
And just wondering, like, because you mentioned like there are two captioners, and they use like 95% of the synthetic, I guess, the output of the captioners. Like, are we talking about like the short synthetic caption, or like do they use like the mixture of short and the descriptive?
They use the descriptive and the ground truth. 95% descriptive and 5% ground truth, which is the human labels.
Oh, okay. So the short one got disregarded.
Yeah, because short is just similar to the human input.
We had a previous discussion about it. It's mainly because if you're using generated captions, exclusively, then you might be trapped into the like super clean format. What if a human being had 5 empty spaces before the text? What if they started with a non-capitalized letter? So mixing 5% in will make it extrapolate a little bit better for formatting or other things.